All right. So we'll get started here in just a minute here. These are all the topics we're going to hit up. I cannot guarantee we'll get through everything on this list. We're going to get through everything on the list. Obviously, you guys have learned a lot over this past year. It's not like I can necessarily cover every single thing that you guys have learned. So these are going to be some of the big principles, and we're going to be kind of going through them. And I like to teach by doing practice problems. That's the main way that I like to do. So that's what we're going to be doing. So if you have any questions about it as we're going through the problems, feel free to ask. Otherwise, we're going to go get started here in a minute. And because we have a lot to cover, I'm going to move a little bit quick, okay? There's no break on this train. So we're just going to keep going. And feel free. That doesn't mean I do want you guys to ask questions, okay? Definitely ask questions if you're stuck, if you're not following something, or if you think I'm making a mistake or something, or even clarification. I'm happy to take questions on those things. But I like teaching through example. This is one of the core things. If you guys some of you have seen me on YouTube, some of the things like that. I love to teach by example, and so we are going to go through each of these topics through the FRQs. You guys should have gotten a link to a PDF that sort of has all my important notes for each unit. We're not going to go through every bullet point. We're just going to go through the questions. But I do highly recommend that you do read through those notes. And yeah, so why don't we just go ahead and get started. And we're going to go through some problems. So here's the very first question. We're starting with kinematics. So this is something you learned at very beginning of the class, and we're going to start with a projectile motion problem. So we'll kind of see how, I don't know how it went for all of you guys in terms of that, but let's kind of review the basic idea here. So in kinematics, what we're trying to do is we're talking about the motion, and we're talking about mainly what I would say the 5 key variables of motion that we discuss in kinematics. Now, I might use the equations a little bit different than the way you guys did them in your class, but I always consider these as the 5 key kinematic variables that we study. This is the displacement. These are the velocities. This is the acceleration and the time. And your kinematic equations relate these 5 variables in some way. Okay? So, like I said, I write them a little bit differently than the AP Physics 1 equation sheets do that you're given. But I'm going to write the main equations that you are given for kinematics. They are equivalent on your equation sheet, but this is the way I like to have my students remember them, because I find that these are a little bit simpler than the way they describe them on the booklet. It's the same equations. I just tend not to put a lot of subscripts in my equations. Now, these 5 variables are the key variables we use to apply these equations. And note that for all of these equations, they all relate 4 of the variables. So what we want to do in any kinematic scenario is we want to list out what we know about these variables, which ones we know. Because when you have a problem, you kind of have a lot to organize in your mind. You have a lot of pieces of information that are kind of thrown at you in a question. And so what we want to do is we want to systematically kind of break down all of the variables that we have in this situation. So let's read through the scenario once, and then we'll kind of start listing things out. So we have a ball of mass 0.5 kilograms initially at rest. This is important. When it says at rest, that means it's not moving initially. Is kicked directly toward a fence from a point 32 meters away, as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second. So it was at rest. He now kicks it, and it's now moving at 20 meters per second at an angle 37 degrees above the horizontal. And they kind of have this picture here. The top of the fence is 2.5 meters high, and the ball hits nothing while in the flight, and air resistance is negligible. Determine the time it takes for the ball to reach the plane of the fence. So what we want to do here is, this is a projectile motion. I always like to do a dash mark of the path of the ball. Now, here's the thing where I don't know. I don't know if the ball is going to go over the fence, it's going to hit the top of the fence, or it's just going to like hit the ground somewhere below that. I don't know that, but I'm just illustrating that to remind myself of generally the motion that the ball is going to take when you kick it like this. It has this parabolic graph, so it has this curve like this, right? The shape of a parabola here. Okay, now what do we want to do? when the motion is like this, it's two-dimensional motion, what you want to do with each of these variables here is talk about both the horizontal and the vertical motion. So I'm going to list both columns of variables, x and y, and we're going to talk about each of these variables when we're doing projectile motion. Now, when we're doing when there's no air resistance, we assume that the horizontal acceleration is 0, and we assume the vertical acceleration is downward at 9.8 meters per second squared, or g. Now, here's a common question that people get confused about is, am I supposed to put positive 9.8? Am I supposed to put negative 9.8? What is that about? Well, it depends on which way you want to say is positive, okay? So for every axis, you can orient whichever way you want, but you must be consistent with all of the variables. For example, I'm going to say up is positive and to the right is positive, okay? So in the x direction, I'm going to say the right is the positive direction. I'm going to say upward is the positive direction. If a problem does not state which way is positive, you are allowed to establish which way you want positive to be. And so I usually draw little arrows just like that to indicate which way is positive. All right, and so then I'm going to say, well, let's look at what we know about here. We know the acceleration is then downward at 9.8 meters per second squared, right? Because it's subject to gravity, and gravity points down. So this would be negative 9.8 meters per second squared. That would be the acceleration due to gravity. It's negative because I said up was positive, and the acceleration is down due to the force of gravity. Okay? What else do I know? Well, I know something about the initial velocity, because I know it's 20, but the 20 meters per second is not just horizontal and it's not just vertical. It has components of both, because I'm aiming it not just up and not just to the right, but up and to the right. And so this is the second lesson that we need to learn, is about decomposing vectors. Decomposing vectors is huge in forces, and we kind of start here. When I want to decompose a vector and it's kind of moving in 2 dimensions, I want to split it into a motion that is both horizontal and vertical separately. Okay, and the way you do that is, look at the vector. It's up and to the right for the velocity. Okay, so what I want to do is I want to draw an arrow that starts here and ends here, but I'm going to make it go right first, then go up like this. Now, the direction of the arrows are super important. Okay, don't ignore the directions that they're going. Okay. I made it too messy when I did that. So just make sure that you have the direction. So it's right and it's up. And the way I think of it is has to start here, has to end here. So I have to follow that path. It's like I'm walking from here to here. So I got to go right and then I got to go up. The arrow is important because the arrow indicates the direction, whether it's positive or negative, based on our axes that we say here. Okay, so there's a component to the right. How do I decide the right component? Well, if this is, the way you read this 20 is it's the hypotenuse. So the adjacent side is 20 cosine 37 degrees. And the vertical side, or the opposite side, is 20 sine 37 degrees. Okay? Sine is opposite over hypotenuse. That's why it's the opposite side is related to sine. Cosine is adjacent over hypotenuse, your SOHCAHTOA. If you're kind of dyslexic, which some of my students have been in the past, some people remember sine is like sin. You want to keep the sin far away from the 37 degrees. So the sin is the one that's the side that's far away from the angle. You want to keep that sin away. All right? So that's how we decompose it. So now these are the initial velocities in the x and y direction. Now this one is to the right, and we said right was positive, so that's the x direction. So the initial velocity to the right is 20 cosine 37. The vertical component of the initial velocity is upward, right? The arrow's upward, and I said up was positive. So this would be positive 20 sine 37 degrees. Okay. What else do I know? Well, I know that I want to know the time it takes for the ball to reach the time it takes for the ball to reach the plane of the fence. So I want to know where when it's here at this point in time. So if I look at its motion, I say, well, it's traveled to the right 32 meters. Okay? So the displacement horizontally is 32 meters. The vertical displacement is actually a little bit tricky. You don't know the vertical displacement because you don't know where the ball actually is. The fence is 2.5 meters high, but I don't actually know that the ball hits that top of that fence or not. So this number I don't want to use in my kinematic equations at this moment in time. Okay. And then that's all the information I think I know at this point. This is all I can figure out at this point. Now, typically, so what do I want to figure out is I want to figure out the time here. Now, in projectile motion, these two times are the same variable. So the horizontal and the vertical variables are completely independent except for the time. The time connects the two columns of equations here. Then I say, what I usually teach my students is, you have 3 pieces of information. If you have 3 pieces of information, you can solve for the other piece. So here I have 3 variables, and I want to solve for t. I have 3 known quantities, and I want to solve for this one. I want to identify the equation that has these 4 variables here. And this equation will work. And now I just plug in the numbers here. So for delta x, I'm going to put 32. It's 20 cosine 37 degrees times t. And then a is 0, so it's plus 1/2 times 0 times t squared. Anything times 0 is just 0. And you just get this number, and you can solve for t by dividing this thing over here. 32 over 20 cosine 37 degrees. Okay, and that's going to be some number, which I'll just use my calculator real quick. I got about 2 meters per second. 2 seconds. Okay, that's the setup for projectile motion. That's how you want to do it. Now, part B, will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the top of the fence will it pass? So how am I going to decide whether or not it hits the fence or not? Is to decide, well, if I figure out how high it is, if I figure out this part here, then I know if it's bigger than 2.5, it's going to go over the fence. If it's less than 2.5, it's going to hit the fence. So I ultimately want to figure out this variable right here. Okay? Now we look at this and we say, well, I have, well, now that I know the time, I can fill in the time in my variables here. So this is now 2, and this is 2. And now that I know the time here, I now have 3 pieces of information. I know V0, I know A, I know T, and I'm trying to figure out the displacement there. And so I want an equation that relates those 4 variables. Okay? And it's the same equation that we're going to use here. This equation right here will work. And I'll say H equals V0t, 20 sine 37 times 2, plus 1/2 times A, which is negative 9.8, times t squared. Sorry, I didn't give myself enough room to write that out. But hopefully that makes sense there. I'm just plugging in the numbers into this equation here. So if I do that real quick, minus 4.9 times, shoot. I got 4.47 meters. Okay, now what does that tell you? Now you got to answer the question. Don't just think about the numbers. You got to think about it in a... Oh, sorry, I had a question here. Would it be better simplified by velocity or best to leave form that they're in? Good question. Whether or not you want to put these velocities like this. When you have numbers, it's fine to go ahead and, calculate the numbers here. Often on the AP Physics 1 exam, you're not necessarily going to be given the numbers. So I like to have you practice, and it's good to practice solving with the manipulations. I know it is easier to just sort of plug in the equations. And in this problem, that would be fine if you're given numbers. But a lot of times you are given just variables for these, and you have to solve them in terms of variables. So you want to be comfortable with the algebra enough that you can solve it symbolically without having to rely on necessarily simplifying it like that. Hopefully that makes sense. That was a good question. Okay. Will the ball hit the fence? So we need to answer the question. So I got 4.47 meters. It's not going to hit the fence. It's going to go over it. So no, it goes over the fence. And they want to know how far above the top of the fence will it pass. That means they want to know the distance from here to here. And if this is 4.47, then you just subtract 2.5. We'll just call it 4.5. We'll just round it to 4.5. That means it's going to be 2 meters above the fence. About 2 meters. About 2 meters. Okay. Cool. On the axis below, sketch the horizontal and vertical components of the velocity of the ball as functions of time until the ball reaches the plane of the fence. Okay, so it reaches the plane of the fence. That's at 2 seconds, so I want to stop here. Now, horizontal component of the velocity. Now, because the acceleration is 0, when we're doing graphs, that means the velocity horizontally is just a constant value, right? So it's whatever 27 cosine 37 degrees is. This was about 16 when I did that. So horizontally, because the acceleration is 0, we would expect the velocity to stay same the whole time. So I would expect horizontally it to stay at 16 meters per second the entire time. And they want you to stop right here because they want it until the ball reaches the plane of the fence, which we said was 2 seconds until that happened. Now vertically, you expect the acceleration, well, we said down was negative, so the acceleration was negative 9.8 meters per second squared. So what we want to do is, that means on a graph of velocity, if you guys remember on your graphs of velocity, the slope of the velocity versus time graph equals the acceleration. Okay? So, what I want is, if this is negative 9.8 in the vertical direction, okay, then that means the slope needs to be about negative 9.8 or negative 10. So let's take a look at here. Well, initially, the initial velocity, what we found here was 20 sine 37 degrees, and let's just compute that. That's about 12. So we know that at time 0, it was at 12 meters per second, right around there. And then the slope should be, you know, going down and to the right of a slope. You can make this negative 10 meters per second squared. Like, that's close enough. So that means every second, it should drop 10 meters per second squared. So I go over 1 second, it should be at 2 meters per second squared. Okay? Because this is starting at 12. So every time I go over 1, it should go down 10. That's what a slope of negative 10 would mean. I go 1, I should go down 10 to negative 8. I don't know, negative 8's about there. And then it would just be a straight line. Why? Because the slope should be constant, because the acceleration is constant the whole time. Like that. Okay. And that's it. So that's a recap of kind of kinematics. That's how I like to do kinematics motion problems. You kind of list out the variables horizontally and vertically. Be careful on the directions here. Okay, so up is positive, right is positive. Just be consistent. You could have redone this entire problem with down as being the positive direction. You should get the exact same answer. Yeah. Okay. Now we're gonna move on to the part where physics begins to fall apart for a lot of people. I'll be honest, is the forces and free body diagrams. Okay. So before we start it, I kind of want to recap some of the bigger rules I like when you're drawing a free body diagram. Okay, so free body diagrams, they're a little tricky, okay? But I want to follow all the rules for every force, and I want to recap all of the forces we talk about when you're approaching a problem. All right, so for a free body diagram, you want to draw an arrow starting at the diagram and pointing in a direction, and there are only a few basic forces we look at. Okay, first force is gravity. Gravity points downward, always points downward towards the center of the earth. Okay, I got it. Let me see. I just want to make sure. Oh, whoops. Okay, so gravity always points downward towards the center of the earth. That's usually the first arrow I draw on any free body diagram. Unless you are far away from a planet, there is always gravity acting on them. Okay, so gravity is always acting downward towards the center of the earth. Now, here's the key part of what I ask you when you're doing the next forces. Every other force requires a physical contact with the object. Okay, so the next forces we talk about, all of them, they all require physical contact. So what I ask myself in a free body diagram, I ask myself, What else is touching the object that I'm drawing the free body diagram for? Okay. There could be a tension force. Tension forces always pull. So whatever the rope is touching, wherever a rope or string is touching it, it is always a pulling force. Normal force is only if you have a surface touching it. It's a perpendicular to the surface. So normal force is perpendicular to the surface and pushes outward, if you want. So we'll go through examples of these, but a normal force requires a surface touching it. If the surface is touching it, the force is always perpendicular. The word normal actually comes from mathematics. Normal means perpendicular. That's why we call it the normal force. Like sometimes when you guys take math eventually and you do calculus, it's we talk about tangent lines and normal lines. Normal lines are lines that are perpendicular to the tangent line. So the word normal means perpendicular. That's why it's really important we draw this perpendicular to the surface. Okay, then you have frictional force. There's two kinds, static or kinetic friction, but in both of those cases, they are parallel to the surface. Again, frictional forces require a surface. And the distinction between friction, static, and kinetic friction is if the surfaces are rubbing, it's kinetic friction. And if it's not moving, if the surfaces are not moving relative to each other, it is static friction. Okay? And then finally, we have spring force. And this follows Hooke's law, which we're not going to get to in this problem, but basically a spring force pulls or pushes whichever is in the direction to make the spring at the relaxed length. So very, very briefly, for a spring force, if I squeeze a spring, it wants to push outward. If I stretch a spring, it wants to push inward. Okay, because springs want to go back to their natural length. Okay, so the direction of the spring force is to the relaxed length. So if you stretch it, it doesn't like it. Like you think of a spring, it doesn't like change. When you stretch it, it's going to pull inward to go back to its relaxed length. And if you squeeze it, it wants to go back, push outward back to its relaxed length. Those are the only forces you should be drawing. Okay? When you're doing a free body diagram, and if you're struggling with this, I would have you heavily rely on these forces and identifying. So I asked myself, I put gravity. I asked myself, what is touching the object physically? And I draw a force corresponding to the type of thing that is touching it. Okay? There is one more force we kind of get into when we do a rotation. That's a force from the axle. It's a kind of normal force, but it has some interesting properties that we'll talk about. But for now, if we're not talking about any rotation at this point, these are the main forces we're really going to discuss. Okay? So those are the rules for free body diagrams. After we do a free body diagram, we apply F net equals ma. And we'll kind of illustrate that with an example here. Okay, okay, blocks 1 and 2 of masses m1 and m2 are connected by a light string as shown above. These blocks are further connected to a block of mass m by another light string that passes over a pulley of negligible mass and friction. Blocks 1 and 2 move with a constant velocity v down the inclined plane, which makes an angle theta with the horizontal. Kinetic frictional force on the block. So when you kind of get all this information, I usually am trying to connect everything that's happening with the picture, right? Pictures are super important. If the problem doesn't give you a picture, you should draw your own picture of what's happening, because that's the best way for you to visualize all this information, because otherwise a bunch of words here. Okay, what are some keywords? Blocks 1 and 2 move at constant velocity. Constant velocity is a key word. In the note packet I linked you guys, there are some key phrases you want to think about. Constant velocity means the acceleration is 0. Okay, and that's going to be important for us when we do this problem, which makes an angle theta with the horizontal. The kinetic frictional force on block 1 is F. So this guy has a frictional force F. This guy has a frictional force 2F. On the figure below, draw and label all the forces on block M1. So this is the free body diagram. This is what I'm going to do. I'm going to follow the exact rules I just listed out. M1. I look at the picture of M1. Well, first I say gravity. Gravity you can write as FG, or I like to write as just M1G. Okay? Now, What is touching block M1? Well, there's clearly a rope touching it, a string here. Which direction is the string going to act? Strings can only pull, and so I got to make it up and to the right, and I'm going to call this T1. Okay, we'll call this T1 here, and this is another rope we'll call T2 for later. This is T1. It's only pulling, so it has to be up and to the right. Why? Because I can't push with the string. Imagine I've wrapped a string around you. I can pull you around, but then I start pushing with you and nothing happens. It just goes slack. I can only pull with the rope. I cannot push you with the rope. So what would be the pulling direction would be up and to the right like that. Okay? What else is touching block M1? The ramp. It's physically touching the ramp here. So the ramp is providing it's a surface. It's a normal force. What's the direction? Perpendicular to the surface like that. Okay? Normal force this way. Okay? Now, is there friction? Yes, they told us there's a friction. Which way is the friction? Friction, the direction of friction, this is kinetic friction, by the way, because it is sliding, right? The block is sliding relative to the ramp. So it opposes that motion. Friction always opposes the motion, and so it's up the ramp, and it's F. Okay? That's it. Nothing related to M2, nothing related to M, because those guys are not touching this object. I am only focused on what is touching M1 when I'm doing a free body diagram. Okay? That's it. So that should be easy if you follow those rules. If you just do like that, boom, that's easy points on a free body diagram. That should be like a, boom, they give that to you no matter what, okay? Now express your answers to each of the following in terms of M1, M2, G, theta, and F. Determine the coefficient of kinetic friction between the inclined plane and block 1. Okay, this sounds hard. This sounds like, how do I even start with something like this? Okay? Well, there's a couple of ways I teach my students to really focus on this. First, when you have this, you're always eventually going to do a net force equals ma. After a free body diagram, we always do net force equals ma equations next. That's the automatic thing that we do. After a free body diagram, we apply Newton's second law of motion. That's like the natural thing that we do next. Okay? But what I like to do is like, how could I figure out the kinetic friction first of all? Well, the coefficient of kinetic friction is related by this equation. Kinetic friction is equal to mu times the normal force. This is just a general term. Okay, so I need the frictional force and I need the normal force. So in this case, mu is equal to the frictional force over Fn for block 1. Well, I already know the frictional force. That's little f. So ultimately, what I need to figure out is what Fn is, what the normal force is. Okay? Like, we're still going to do Fnet equals ma of the free body diagram. Okay? We're almost always going to do that. But this gives you a little bit of concept of what am I looking for? I am ultimately looking for the normal force to help me answer this question. Okay? So what do we do now? Well, on an inclined plane, we want to split so you always want to split the vectors into horizontal and vertical, just like we did in the kinematics projectile motion question, where I made the velocity, I took the horizontal component and the vertical component, right? Oh, okay. Someone was asking, I'll answer this one live. Someone was asking, why was friction in the same direction as the tension force? That's good. Okay, so when you are sliding down the ramp, okay, so something is sliding down the ramp. I hope you guys can see my video, hopefully it's not too small. If something is sliding down the ramp here, because they told us that, what did they tell us? Blocks 1 down the inclined plane here. It's moving down the ramp. Friction always points in a direction that opposes the motion. Okay, so like if it's sliding down the ramp, the force is up the ramp on this block because the block is trying to go down the ramp, and to oppose that, we would push up the ramp. Okay, so I hope that was clear. Good question. All right, so what we were doing is we want to decompose the forces into horizontal and vertical components, just like we did on the projectile motion when we're kind of clicking at an angle there. Like when we were doing the projectile motion, we did the velocity. Now, how do we do this? On an inclined plane, it's much easier if you kind of say like, oh, well, this is my x direction and this is my y direction. It's to make the math easier if you do it that way. Okay, that's the only reason I would tell you. Technically, you can do it any direction, but we're going to say this is the horizontal direction, and then perpendicular to the ramp is in the vertical direction. So if you look at that, tension in F and Fn are always in the x and y direction, but M1G has components that are both in the x and the y direction. So you would draw a vector like this. And remember how I talked about decomposition. You want to make a right triangle. I'm actually going to redraw this a little bit bigger so you guys can see it a little clearer. This is MG, and this is, my axes look like this. This is the y direction, and this is the x direction. I want to make a right triangle. My goal is to make a right triangle, one that goes in this direction and one that goes in this direction. And remember, the arrows are super important. It is important the direction that the arrows are going. So I want to make it go, I want to start here and end here. So I want to make it start here, go this way, then go here, and this is a right angle. Now, this angle ends up being the same as theta, as the same as the angle of incline, okay? I don't really want to prove that to you. It's just, you can if you want, but it's just, you just kind of remember that fact. So this is the hypotenuse. This is the adjacent side. So this side is mg cosine theta because it's adjacent. And then this side is mg sine theta. All right. Now, just like in projectile motion, we're going to set directions to be positive and negative. I'm going to say down the ramp is positive, and I'm going to say perpendicular to the ramp is positive here. Okay. Oh, let me draw the other forces here. So let's draw this one just to complete it. This is T1, this is F, this is Fn, and those are all the forces. I'm just redrawing the forces from here onto this slightly bigger picture. Okay, so now I've established which way is positive, negative. Now I'm going to do net force equals ma. But I want to do it in the x and the y direction. So I'm going to do the x direction and the y direction. Just like in projectile motion, we kind of split it up into the x and y directions. We're going to do the same for the F net equals ma. Newton's second law. Net force always is from your free body diagram. Okay, so the x directions, I'm going to circle these in purple. Which forces are parallel to the ramp? This one, and this one here. Because look at the arrows. Those arrows are parallel to the surface there. Okay? Now I'm going to establish signs. Well, down the ramp is positive. That means mg sine theta, which is pointing down the ramp, is positive. T1 and F are up the ramp. Those are negative. And those are the only horizontal forces, so that equals m1 times a. Now in this problem, we just said at the very beginning it's constant velocity, so a is 0. So this is actually equal to 0. Okay, that's one equation. I'm not going to solve anything yet. I'm just going to leave it alone for now because I want to think about big picture. What am I trying to figure out? I'm trying to figure out the normal force, right? This is not going to help me figure out the normal force, or at least there's no obvious way it's going to help me figure out the normal force. So then let's focus on the y direction. And these are the forces that are in the vertical direction. Fn here and mg cosine theta. Those two vectors are pointing in the y direction. So I'm applying F net equals ma in the y direction. I said out of the ramp was positive. That means Fn is the positive force. What else is and then mg cosine theta, which is down, opposite direction, would be negative. And that equals ma. The acceleration is still 0, right? Because if the a is 0, then m times a is going to be 0. So here I can see Fn is just moving this to the other side. Fn is mg cosine theta, which is what I wanted here because my goal was to figure out what mu was. Mu was little f over Fn, but now I know what it's mg cosine theta is here. And I always double check. Am I allowed to use, I'm only allowed to use these variables. I only used f, mg, and theta. I should put, which m? Yeah, this is m1, right? I didn't write that on here. These are m1g. So I should put m1. So good thing I checked that because it's like, what is m? It's m1. Why is it m1? Because I'm doing a free body diagram of m1, right? So this is all m1 there. Okay, cool. Determine the value of the suspended mass m that allows block 1 and block 2 to move with constant velocity down the plane. Okay, so now they're asking us about something else. They're now asking us about this block over here. And they're asking, well, what mass do I need here? Well, this is a little bit tricky. Okay, what mass do I need here? There's kind of a, yeah, so what I would do here is if I'm being asked about another object, I would do a free body diagram of this guy. So, what are the forces acting on M? Well, I would start with gravity, big mg. What is touching the block? This rope here. There's a tension here. I'll call this T2. And it pulls. It can only pull up. Nothing else is touching that block. So that's everything. That's it. Okay, so what can I do here is I can say, oh, well, I can do F net equals ma again after I have this picture. And I say, well, I know the acceleration is 0. Let's just say up is the positive direction and down is negative for this guy. So when I do my net force, T2 is upward, so it's positive. Mg is downward, so it's negative. So I'm just adding those forces, and this is 0. So I get T2 is equal to mg. Okay? Not particularly helpful yet, but like I need the m to go somewhere, so I need to figure out what T2 is. So maybe I have to look at this guy, block 2. So now I'm going to do a free body diagram of block 2. Block 2 is the most complicated free body diagram. Okay? So this is, I'm going to put M2 right here. What are the forces acting on this guy? And I'm going to do this one a little faster because it's very similar to block M1, but I got gravity going down. Always put that down. What's touching it? T2 is pulling it up and to the right. T1 is pulling it down and to the left. Why? Because T1 is touching it. Those are the two ropes doing it, and they can only pull. Right? It's kind of weird that T1's pulling on this guy and he's pulling on this guy. That's fine. They're pulling in different directions on the two different blocks because they can only pull. All right? So T1 is down the ramp, T2 is up the ramp. The normal force is this way. This is a different normal force. I'm going to go Fn2 because it's the normal force on block M2. And then I have a frictional force 2F. Again, because block 2 is sliding down the ramp, 2F goes up the ramp like that. So that's the free body diagram of M2. Okay. Similar to this one, I'm going to decompose it into this component and this component. This is M2G sine theta. And this side here is M2G cosine theta. All right? Because this is theta here. Exact same thing we did right over here. It's just now this guy has a T1 down here pulling it. But that's because there's a T1 touching him, and that's it. All right. Now I'm going to do net force equals ma in the horizontal direction. I'm going to scroll up for this just to give you a little space for me to... yeah, let me... so what I'm going to do is actually I'm going to take that text and move it down here. So I can write out some equations here. So I want to highlight some equations that I know so far, right? Because a lot of this is bookkeeping, a lot to keep track of. T2 is mg, and then I have some equations over here that I want to keep track of. Okay, these equations are important equations for me. So this equation, if I look at this one, I say, well, let's say down the ramp is positive and up the ramp is positive. We're going to do net force equals ma. I'm only going to focus on the x direction right now because I know that I only care about T2. I don't really care about the vertical direction. So if down the ramp is positive, I would say T1. So which forces are down the ramp? Let me circle them, or in the x direction. This force is in the x direction. This force is in the x direction. And these two forces are in the x direction. T1 is down the ramp, and I said down the ramp is positive. M2G sine theta is also down the ramp, so it's positive. T2 and 2F are up the ramp, so they're negative. And again, this acceleration is 0, so I just kept make them equal to 0. So I have this equation. So I want to list out all the equations I have. I have this equation. I have this equation from over here. And I had T2 is equal to mg. These are the equations that I had. And what's the big picture? So yeah. So Felix had a question here. Could you draw M1 and M2 as a system so it eliminate T1 and T2 with just one T, which equals mg? You can draw it. You can group these guys as a system if you wanted to do that free body diagram. That would work. System free body diagrams are sometimes a little bit tricky. I want you to be able to know how to do both ways, I would say. But yes, if you wanted to group these guys up as a single object, as a system, and then you would just have T2 and you have these two objects. You'd have to keep in mind, though, if you did it that way, you have both frictions to consider. Okay, so you'd have 3F acting up the ramp. Okay, we can talk about that in a second, actually. That might be a good illustration of this. But when we have these equations here, what I want to do is, my goal is to figure out M. So I'm going to plug that in for T2. Okay, so then what I would do is, this equation would be T1 plus M2G sine theta minus mg minus 2f equals 0. And then for these two equations, I'm just going to add them because I want to eliminate the tension. Why do I eliminate T1? Because I'm not allowed to use T1. T1 is a variable I made up. I'm not allowed to use it in my answer here. So if I add these two equations, right? So this is about solving systems of equations. If I add these two, the T1s will cancel. So if I add the left sides, then it'll work. So this will be m1g sine theta minus T1 plus T1. Those will cancel. Then plus m2g sine theta minus f minus mg and minus 2f equals 0. I'm just sort of adding all of these up together on this side, just adding the two equations. And now I can see that I have m1g sine theta plus m2g sine theta minus 3f. I'll move the mg over to the other side because I want to solve for m. And so I want to isolate m. So I added mg over there, and I just divided by g. And boom, that's my answer for m. Okay. Now, someone had a good question about whether or not you could treat it like a system. I do want to illustrate that because that's a point. So sometimes you might want to combine objects into a system and just do a free body diagram of this M1 and M2. Okay, so if you wanted to do that, which is fine, you can. T1, any forces T1 would be internal to the system. So you'd have to be a little bit careful because you'd have M1G going down, gravity on this guy. You'd also have M2G going down. You'd also have T2 touching this system. So when you're doing the touching part, you say what is touching the system? So imagine I put a little, I just make this a blob and I just shade it in like this. So there's an M1 and an M2 in there. There's also 3F going up the ramp because on M2 there's 2F going up the ramp, and on M1 there's an F going up the ramp. And then you would have some kind of FN force here like this. So you could do it, and that's how you would draw the free body diagram of a system. And you can do the exact same things on this, and you should get the exact same equations that you get down here. Okay. And then part D is, if I cut the string now, I cut this string, determine the acceleration of block 1 while it's on the inclined plane. So now, with M1, you go back to your M1 free body diagram, and you say, well, what has changed now that I've cut the string? Well, now the acceleration is not 0, okay? And I now have removed the tension force. Like, that force is no longer there. Okay, so then my free body diagram for M1, all that's changed really is now I have an M1G down. I have an F going up, and I have a normal force this way. All I've done from the free body diagram is I've cut the rope, so the rope is no longer has a tension. There's no rope touching it anymore. I've cut it, and boom, it's just sliding down like that. But the acceleration is not 0, so I can't assume the acceleration is 0. I'm still going to write this out just like we did before. This is M1G cosine theta. And now there's an acceleration down the ramp. And if you look at the net force down the ramp, you say down is the positive. I do F net equals MA. What forces are down the ramp, or in the x direction? So we're doing the x direction here. M1G sine theta is down the ramp, so it's positive. F is up the ramp, so it's negative, and that equals M1A. And so you can solve for A. A would just equal this divided by M1, because the M1s would cancel. And so that's the acceleration. That's part D. So the key thing about these is when you're drawing the free body diagram, it's important to get that right, and it's important to apply F net equals ma, and it's important to have the correct directions be the positive and negative directions. Which way is positive, which way is negative. Okay. Cool. Circular motion. Circular motion is a tricky one, but here's the big things that we're going to talk about in circular motion. 1, free body diagram is not any different than anything we just talked about. You do not draw the free body diagram any differently just because it's moving in a circle. Okay? That's the important thing. What is different in circular motion is the kind of acceleration that you're having. So the acceleration, rather than being linear, okay, going up and down the ramp or just speeding up or slowing down, is the acceleration is changing the velocity, the direction of the velocity of the object. Okay? If the direction of the, like so for example, as it's moving through a circle, the velocity is like this way, then this way, then this way. The velocity is tangent to the circle, okay? Because that's the direction of the motion, is tangent to the circle. Okay, the velocity is changing directions. When the velocity is changing directions, we call that a centripetal acceleration. Because remember, acceleration is the change in velocity over time of an object. So if there's a change in the change in velocity, because velocity is a vector, right? So if it changes directions, there's still a change just because it didn't, go faster or slower. It's still considered a change. That is subject to an acceleration, and we call that the centripetal acceleration. So in practical sense, the free body diagram we do is exactly the same. It follows the exact same rules we just talked about. No other forces than what we just listed, except now the acceleration, there might be an acceleration towards the center of the circle called the centripetal acceleration. So when it's moving in a circle, the centripetal acceleration moves perpendicular to the moves towards the center of the circle. So AC is a new concept. That's the only new concept in circular motion, centripetal acceleration. And it's pointing, it's towards the center of the circle. And it's equal to v squared over r. Okay, I'm not going to derive that for you. That's just something you just know as a fact, okay? All right. Now let's take a look at this problem and kind of see how we go through that process. Just keeping in mind everything we're going to do. Oh, someone has a question. Why does centripetal acceleration always point towards the center of the circle? Okay. One is by definition, but in terms of what that means is, so if it's going toward, so you have to think about the change in velocity. So think about this vector. The velocity, like consider from this point to say this point where the velocity is going this way. The velocity was this way, then the velocity became this way. Okay, this is the new velocity. Like it was going up and to the left, and now it's going left. Okay, so what is the change in the velocity? The change in the velocity is this arrow right here. This is what we call the change in velocity. Why? Because this velocity plus this velocity gives you this velocity here. That's about vector addition. So the change is down and to the left, so to speak. And that is always going to be perpendicular to that original velocity. And because acceleration is the change in velocity, and divided by time, right? But because the change in velocity is that direction, the acceleration is in that same direction too, perpendicular to that original velocity vector. So that's why the centripetal acceleration. Now, it doesn't mean that the only acceleration is centripetal, okay? It just means that the component of the acceleration that causes it to change directions has to point at a right angle. For example, if I want to go straight and then I want to point this way, I need to push on it like to the right. I need to push perpendicular to point it a different direction. So in the same way, the acceleration is perpendicular for that reason, because it needs to push the velocity vector in a different direction. And that acceleration is always perpendicular to that velocity vector. Okay? Any component of acceleration that is parallel to the velocity would cause it to speed up or slow down. And we don't call that centripetal acceleration. We call that linear or tangential acceleration. That's when you're like the normal things prior to circular motion, things are speeding up or slowing down. Okay, so let's read this problem and let's talk about it here. I hope they answer the question. If it doesn't, just let me know. Ball of mass m is attached to string length L, moves in a circle in a vertical plane as shown above. At the top of the circular path, the tension is twice the weight of the ball. That means right up here, the tension is equal to twice the weight of the ball. A couple of things. Weight of the ball is just mg. Okay, if you didn't know that, weight is always just the force of gravity. Those are the same things. So the tension here is equal to 2 mg. That's what they're telling you right there, right up here. Okay? At the bottom, the ball just clears the ground. Air resistance is negligible. Express all answers in terms of m, l, and g. Determine the magnitude and the direction of the net force in the ball, what is at the top. Okay, if I'm asking you about forces at the top, you better draw a free body diagram. Okay, I'm like angry at my students. Not really angry, but I'm disappointed in my students if they're asked about forces and I don't see a free body diagram. You must do a free body diagram. Okay, so right up here, this guy up here. What are the forces acting on it? Same exact rules that we talked about in the previous unit. I start with gravity. Gravity points down towards the center of the earth. What is touching the ball? The rope is touching the ball. Ropes can only pull, so the tension is downward. That's it. Nothing else is touching the ball. There are no other forces on the ball. That's my free body diagram. What's the next step? F net equals ma. Well, actually, they're just asking magnitude and direction of the net force. Well, these two forces are both downward, so when you add them up, it's going to be downward. I know T is equal to 2 mg, so when I add the forces here, it's going to be T plus mg, assuming down is positive. That would be, but I know T was 2 mg, so this is just 2 mg plus mg. That is 3 mg. Okay? So I also want to say downward, because they ask you magnitude and direction. It is downward. Determine the V0 speed at the top. Well, that's just one more step from the F net equals ma. We almost, if you draw a free body diagram, you almost always are going to do F net equals ma next. Okay? The Newton's second law of motion. So net force is 3 mg. Mass of the ball is m. Now here's the part that's different for circular motion. What kind of acceleration is it experienced at the top here? Centripetal acceleration, because it's moving in a circle. That centripetal acceleration is equal to v squared over r. So instead of a, I put v squared over r, the centripetal acceleration. Okay? So they called it v0 here. And r, instead of r, right, because r is the radius of the circle, the radius of the circle is L. So instead of r, I'm going to put L instead. But it's the same thing, v squared over r. It's just in terms of the context here, it's that. And then I just want to solve for v. So cancel the m's to both sides. I'm going to multiply by L. So v0 is square root of 3lg. Square root of both sides to solve for v0. Okay? The string is then cut when the ball is at the top. So at the top, the string is cut. So what's changed now is there's no thing here. But it was moving with the speed v0 here. So now it's moving at v0 horizontally, right? Horizontally because its velocity was tangent to the circle. So what kind of motion is this going to be? Like what's going to happen? It's moving to the left. Now it's not subject to any, no string or anything. It's just subject to gravity. That's going to be a projectile motion problem. Okay? So now we're going to set this up as a projectile motion problem, but with variables. So now we're revisiting projectile motion as a practice. See, in a free response question, you have no idea what the topic's going to be. And this one is a projectile motion for this part here. So what are we going to do is we're going to do the x and the y directions. I'm going to list out all the variables that I use for this. As a tip for projectile motion, the time is almost always the y direction, but let's just do that. Let's say, this time I'm gonna say down is positive, okay? I'm gonna say left is positive, down is positive. Direction's really important when you do projectile motion. You wanna get the signs correct, okay? So the initial velocity here, or let's just start with the accelerations. I'm gonna do the accelerations first. Acceleration 0, always in the horizontal direction. The vertical direction, the acceleration is downward at g. So because down is the positive direction now, I'm gonna make this g. I'm not gonna make it negative g. Negative g is if I said up was the positive direction, okay? But since I said down was the positive direction, then I'm gonna use positive g for the acceleration. Now the initial velocity in the x is only horizontal and it's to the left. So it's equal to what we got here, the square root of 3lg. But there is no vertical component to this velocity. Like it's only, like right at the top here, it's only moving left, so the initial vertical component is 0. Okay? And then what else do I know? I want to know the time it takes to hit the ground. Well, I know the vertical displacement because I know that the distance from here to the ground is about 2L. Right? So I know the object is going to fall 2L. It's going to end here. It's going to fall a distance of 2L. Downward is the positive direction, so the displacement vertically is 2L. Because down is positive, and it's moving downward, a distance 2L. Like, notice here, I don't care about the horizontal distance, because when I'm doing the vectors, I only care about the vertical distance displacement there. Okay, now I want to know the time here. So I want an equation that relates these 4 variables right here. And it's almost, for projectile motion, it's almost always this equation. So I just plug in 2L. This is 0 times t plus 1/2 gt squared. Anything times 0 is 0. Going to multiply by 2, divide by g. So that'd be 4L over g equals t squared. And then I just take the square root. Oops, 4L over g is equal to t. That's the time. We can move that to that side because the time is the same on both sides. And so the next part is to determine the horizontal distance. That means they want the horizontal displacement. It travels before hitting the ground. We're going to use the same equation. Now that I know the time, I can use the same equation here. The v0 is square root of 3lg. And the time is square root of 4L over g. Because the acceleration is 0, this part doesn't matter. So then I can just put them all in the same square. When you multiply square roots, you can put them all together. 3lg times 4L over g. G's cancel. That becomes L squared. Square root of 12L squared. And if you want to do that, that's square root of 12 times square root of L squared, or just L. This is not a math class. You don't have to simplify it that significantly. Okay? All right, cool. So, I probably have to pick it up a little bit because we are just through the 3rd module, so we're not quite halfway and we're almost at an hour in, but hopefully everything's been making sense so far. Okay, next we're going to do work and energy. Okay, so this is the big things you want to talk about in terms of work and energy. Work, okay, work is a force times the displacement, okay? Now, the key thing about when you're calculating work is the force and the displacement have to be parallel to each other. So sometimes we write it as force parallel. And instead of displacement, like displacement is technically the word you should use, but sometimes people use d instead of delta x. Doesn't really matter. Just like you might see it as like F parallel to d. And that is sometimes written as F delta x cosine theta or FD cosine theta. Okay. Conceptually, the important thing I want you to really think about is force. For work to happen, a force must move in the parallel direction as the displacement. Okay. So there's a couple of things. For there to be work, it has to move, has to actually travel, and you actually have to apply a force. Example: suppose I'm trying to push my car and it's not moving. Well, even though I feel like I'm putting a lot of effort in, I'm pushing really hard, and the car is not moving because I'm not strong enough to make it move, even though I'm exerting a lot of effort, that work is 0 because the displacement is 0. The car has not moved, right? There's no, like, in mechanics, we require work to require a force in the direction or parallel to the direction that the object is moving. Okay? So that's one thing. One, it needs to move for there to be work. Second, the force must be in the direction of the motion. Okay? That means if the force is perpendicular to the direction of the motion, there is no work happening. Okay? That's one thing to keep in mind. I'll say it again. If the force is perpendicular to the direction of motion, there's no work happening. Okay? The force must have a component parallel to the displacement. I usually don't have students really worry about this equation too much. I really have them think about this. The force must be parallel to the displacement. So that is what work ultimately is. Now, if force and the displacement are in the same direction, it's positive work. If the force and the displacement are opposite directions, it is negative work. Okay? That's a key thing in mind. So if you ever get a question that asks you, is the work positive or negative? Justify your answer. What you have to decide is the force and the displacement in the same direction or if they are in opposite directions. Okay? That's a key part about whether work is positive or negative. The other big principle is that work causes a change in energy in a system. Okay? The way I think of it, work causes a change in energy of a system. So this is a key part. You know, change in energy, this triangle means change. It means E final minus E initial, if you want to think about it that way. Some people don't deal with that triangle. Work is the final energy minus the initial energy. That just means change. It means here's the energy, here's the new energy, here's the old energy. The difference is the change in the energy. Work causes a change in energy in the system. Now, what is energy? Well, there are actually 4 forms of energy we talk about in mechanics. 4 mechanical forms of energy. We talk about kinetic energy. And we've been talking about just translational kinetic energy. This is equal to 1/2 mv squared. This is if an object is moving at all with any speed. Then it has translational kinetic energy. We have gravitational potential energy. The rule for gravitational potential energy is you have to include the Earth in the system. So Earth must be included in system. One thing I wanted to note, this MGH is only true when you're near the surface of the Earth. When you're further away, like let's say I'm like out near Neptune, all right, the gravitational potential energy with the Earth is not MGH. It's not like super huge like that because gravity doesn't extend, you know, like an infinite distance. Well, like it weakens as you get further away. So this is this formula is the very common formula we are going to use most of the time, 95% of the time. But if you're talking about like planets or far distances, then you should use a slightly different equation, which is negative g m over r squared or something like that. Mass of the Earth over the distance. Anyway, I'm not going to focus too much on this one for today because that's like less commonly used, but that is a different form of, I just wanted to note that, and that's noted in the notes that you guys have. Okay, you have a spring potential energy. And this is if you stretched or compressed the spring, 1/2 kx squared. Okay? And then the last energy is when we deal with rotation. So we're not going to talk about it right now, but it's rotational kinetic energy. And that's when something is spinning or rotating. That's 1/2 I omega squared. Those are the main forms of mechanical energy we're going to talk about. So this one, I picked this problem because we got 3 forms of energy in here. We got gravitational potential energy because we're changing heights. It's going to be moving. There's going to be spring potential energy, all forms of energy. So it kind of really stresses, I would say. Yeah. Someone asked a question about sending the notes again. It's in the Zoom link, the link you used to click on here to join this session. There should have been an attachment link, but I will send it again when you guys get a link to the recording. Okay? So someone was asking about sending the notes again, so I just want to. So that is, I'll include that in the email that has the link to this recording here. Okay, so we have a 2 kilogram block dropped from a height of 0.45 meters above an uncompressed spring as shown above. The spring has an elastic constant. Spring constant is the old terminology. It's spring constant of 200 newtons per meter and negligible mass. The block strikes the end of the spring and sticks to it. Determine the speed of the block the instant it hits the end of the spring. Okay? Now, you could do this one by kinematics, by the way. You could say, like, how fast is it going here? How fast is it going here? But we're going to actually use principle of conservation of energy in this system. Conservation of energy says if there's no work happening, there's no change in energy. Like, if you look at this equation, if work is 0, if W is 0, then EF equals E0. Right? The final energy equals the initial energy. And we're going to focus on that aspect when we're solving these kinds of problems here. Okay. So why is there no work being done? I want to illustrate this because you have to, a lot of times on the AP Physics 1, it's not this kind of calculation-based stuff. I do a lot of calculations with you as a means to understand the principles that we're applying, right? So why is it that I can do conservation of energy? Why is there no work being done? Well, if I draw a free body diagram right now, the only force acting on it is mg. Okay, it's the only force acting on it. Nothing else is touching the block, right? So there's no other forces on the block. However, you might say, well, you know, it's falling and mg is going down. Why isn't there work happening? Well, that's why we include the Earth as part of the system. If we include the Earth as part of the system, then we're basically saying that this is an internal force to our system. Okay, we just said like, oh, that's internal to our system, so I don't need to worry about that force doing work. It's internal. Okay, so that means this guy doesn't do work because he's internal to our system, but so there's no work being done, so the energy is conserved. Okay. So that's the big idea on that one. That's why we include the Earth as a system. If you did not include the Earth in the system, then I cannot say the work is 0. I would have to say work is causing a change in energy of the block. Okay? And the change in energy is giving the block kinetic energy, by the way. But let's do conservation of energy. So what's the energy here? Well, when you're doing energy, you always, potential energy especially, you want to consider a reference point. So I'm going to say the reference point is h equals 0. You can pick anywhere to be your ground point, the point where there is 0 potential energy. Okay? That is arbitrary. A lot of times we pick the lowest point in the problem or the surface of the Earth. In this scenario right now, I want to make h equals 0, this part right here. Okay, awesome. So what's the energy at the top down here? Well, I ask myself, does it have any speed at the top? Well, it is dropped. Whenever something is dropped, the speed up here is 0. Okay? Because it's not like I threw it down. I just let it go. Okay? So it doesn't have any kinetic energy, but it does have gravitational potential energy. So I want to add up all the energy. So I would say there's no kinetic energy. There's potential energy. So I'm going to say there's mgh, which is 2 times 10, if I use g of 10, and the h is 0.45. And so that would be 9, I think, 9 joules. Yeah. Okay, how about down here, when it's colliding right here, and right when it hits this thing? Well, now when the block is down here, the height is 0, so it has no gravitational potential energy, but it does have kinetic energy. So then I would say, oh, so that's equal to 1/2 times 2 times v squared, which is just v squared. And I know that has to equal 9, because that's to equal the initial energy by conservation of energy. So v has to be 3 meters per second. Determine the force in the spring when the block reaches the equilibrium position. Okay, this is a terminology you're going to do. What's equilibrium position? Equilibrium position is where the net force is 0. Okay? That's what equilibrium means. So what happens is now the block is now sinking and sinking and sinking, and it hits a point where the net force is 0. So I want to draw a block here, and I want the net force to be 0. Well, I got to draw a free body diagram. The net force is 0. I should draw a free body diagram if I'm asking about the forces, because I'm asking about the force in the spring. Well, I have gravity. What's touching it? Spring's touching it. What have I done to the spring? I've squished the spring, right? So the spring wants to get back to its unsquished position. So it wants to push upwards on me, right? I've squished the spring. The block is sunk, so the spring force is acting upwards. I know the net force has to be equal to 0. So I say, we'll say up is the positive direction. Doesn't really matter. So that means then I do F net is just the spring force minus mg, because up, spring force is up, mg is down. So that's the negative direction. FSP minus mg has to equal 0. So the spring force just equals mg. And that is 2 times 10, which is 20 newtons. Okay. The distance that the spring is compressed at the equilibrium position. Okay, how do I do spring compression? That's related to Hooke's law, which we didn't really talk about, but the spring force is equal to kx. K is the spring constant. X is how much the spring is stretched or compressed. So there's a new equation. This is called Hooke's law, right? And that relates the force on the spring based on its displacement. So I know that this is 20. I know K is 200. So how much is it being compressed? 20 divided by 200, which is 0.1 meters. So that means at the equilibrium position, so let me draw the block at the equilibrium position right here. It's now at 0.1 meters. Determine the speed of the block at the equilibrium position. Okay? So I want to know how fast he's moving at this point. Now, I knew at this point he was moving at 3 meters per second. 3 meters per second. And now I want to know what he's doing here. Well, again, we're going to do conservation of energy. But this time, I'm going to include the block and the earth and the spring as part of my system. So that even though the spring force is acting, we're going to say that the work is 0, because now I'm saying, oh, the spring is part of my system. So both of these forces are now internal forces. They don't do work, right? And so we can do conservation of energy if the work is 0. I really want to emphasize that point. You don't just do conservation of energy just because you feel like it. Like, it has to be justified by the fact that the work being 0 in a scenario. Okay? So I'm going to make this my h equals 0 point. The equilibrium position will make the new height is 0. And I want to compare, I'm going to erase this just so you guys, just to have a clean slate of what's happening. And I want the energy at this point, and I want the energy at this point. Okay, initially, so now I have 3 energies to keep in mind. I have to think about gravitational potential, I have to think about kinetic, and I have to think about spring potential energy. So the initial energy up here, like he's moving at 3 meters per second at the very top. So it does have kinetic energy, has 1/2 mv squared. It has gravitational potential energy because I'm saying h equals 0 is right here. So it does have some mgh. But it has no spring potential energy because the spring has not been compressed yet. When the block is here, the spring is fully in its relaxed length. Then down here, the gravitational potential energy is gone because now the block is at height 0. It still has some kinetic energy, and it has now some spring potential energy. Okay? Because the spring has now been compressed. So I want to fill in some of these numbers here. The initial energy was 1/2 mv squared plus mgh. So what do I know about this one? It's 1/2. Mass of the block was 2. The velocity was 3. Mass of the block is 2. G is 10. Now the h that I want to use up here for E0, the h is this distance here. The distance above my h equals 0. So that's 0.1 there. Okay. So this is 9 plus 2, which is 11. Now what's the final energy? Well, it has some kinetic energy. 1/2 mv squared plus 1/2 kx squared. The m is 2. The velocity is unknown. I'm trying to figure that out. The 1/2 kx squared, well, the k is 200. They gave that to us in the problem right there. And then the x is how much the spring has been stretched or compressed, which we just found, which is 0.1. That equals 11. Okay, so we simplify 1/2 and 2 cancel. Just use a calculator for that. 100 times 0.1 squared. I think that's going to be 1. So v squared, subtract the 1, v squared is 10, so v is square root of 10. 3.16 meters per second. Okay. A couple of things I want to note about this problem with this thing that I want to emphasize to you guys, especially on the exam. There's going to be times where it's going to be like, oh, I can't get this one because I can't get this one. Or if I get A wrong, then I get B wrong because I used the wrong number, or I get C wrong or D wrong. One thing to keep in mind is if you mess up at the beginning and you get the wrong thing, they don't propagate that error forward. If you apply the correct logic with an incorrect number from a previous step, you can still get full credit as long as you are doing the correct analysis based on your incorrect number. Okay? So it is okay as long as you are consistent with your answer. So there's a couple of things that you want to focus on in the AP exam is you don't want to get too stuck on the first part of a question or any part of a question. If you can't derive it or you can't get an answer, put down some things that like talk about some equations that explain what you might try to do to get that answer. Okay, like what principles you want to apply. And then just pick an answer and then just go forward. Like in this instance, you just make up a number and keep going if you couldn't figure it out. Because you don't want to waste all your time on the one part and not put anything. You can still get a lot of credit for the latter parts, even though the previous one is wrong. It's not like you get, let's say with A, I got like, I got it was 2 instead of 3. Well, then obviously, based on my calculations, B and C and whatever are going to be, like, or B might not be different, but C is going to be wrong and D is going to be wrong, right? But that's okay. If I did the correct process, I would actually get full credit for, like, C and D or B and D, even if I got A completely wrong. So keep in mind that if you are doing a problem, don't get too caught up on the early steps. There's a lot of cases where people lose a lot of points because they don't think they can do the derivation, so they don't do the next parts of the question. Okay? Do the next parts anyway. If you leave it blank, you're not going to get any points. Of course, they can't give you any points for that. But you can get credit as long as you put... So always put something for every part of a question. And so that also means don't spend so much of your time trying to get that first part right, thinking that you need that right to get the rest right. You do not need that part right to get the rest right, okay? As long as you're consistent. Okay, someone had a question here. So is the distance that the spring compresses at equilibrium half of the amplitude? If so, can you use mgh equals 1/2 ka squared and just divide from 2a to find the answer C? That's a good question. How do you know what the amplitude is? What's the amplitude? Well, the amplitude would be the motion of it oscillating back and forth. You don't know what the amplitude is, though. Right? Like what would the amplitude be? Right? So that's the hard part. Is to like you don't know the amplitude. Cuz you dropped it here. So this is not this is not the amplitude here because like the spring's not involved in that scenario. So what your suggestion is to take half the amplitude as like what the distance it is. But this is not the amplitude. This is not the endpoint of the amplitude. Why is it not the amplitude? Because at the amplitudes in harmonic motion, the speed should be 0. Speed's clearly not 0 here, right? So what's going to happen is if it sticks there, it's going to go down and it's going to go higher than it originally hit at. It's going to go boom, boom, boom like this. That's the issue. So that wouldn't work. Okay. Determine, is the speed of the block maxima equilibrium position? This one is a little tricky to answer. We actually answer with this one from forces. Okay. So it is maximum at the equilibrium position because if you think about above here, then the accelerate, like if you think about above at the equilibrium position, the acceleration is 0. Why? Because the net force is 0. Above the equilibrium position, the acceleration is down. And below the equilibrium position, the acceleration is up. So where the acceleration is 0 is the maximum velocity. I could explain that with calculus a little bit, but you just kind of trust me. If the acceleration is going from positive to negative, if it's changing directions on the net force, then it's maximum right at the equilibrium. Okay. All right. Let's move on to momentum. Momentum and energy are extremely, extremely closely related. So we do, like this one's going to involve energy and momentum. The idea of conservation of momentum in general is if you have this is the idea, is we have this equation. This is called impulse causes a change in momentum. And we use the letter P to indicate momentum. Now, a lot of times the mass doesn't change, so we just call this m delta v. But I prefer to think of it as this one. This is really what it's supposed to mean. Sometimes we do that one. But it's really the change in momentum of the system. So, but the consequence, just like with if there's no work on a system, there's no change on energy. If there is no impulse, that is to say F delta T equals 0, then there is no change in momentum. The change in momentum. That means the final momentum equals the initial momentum. And we call this conservation of momentum. So why can I apply conservation of momentum is, if I'm ever asked that, or why am I allowed to use conservation of momentum, is because the impulse must be 0. Right? I can only do it if the impulse is 0 in that scenario. Okay? So this is what you want to ask yourself. Now, a lot of times in collisions, we will talk about how the impulse is 0. So in a collision scenario, the way you want to think about it is, if two objects collide, they clearly push on each other. I don't want to say that there are no forces. You want to be very careful on here. When I have two objects collide, clearly they are pushing on each other, right? Like if I punch my fist to the wall, I kick a ball, I feel it, right? There's clearly a force happening on my foot when I kick the wall, or when I punch the wall, or I kick a ball. I feel a force. There is definitely a force. However, if we say the system is both objects involved in the collision, that is to say, if I say like me and the ball are one system, then even though there's a force acting on the ball and the ball's acting a force on me, there is no external force acting on that system. So the key part of that is, if we say that the system is both objects involved in the collision, yes, they exert a force on each other. There is no external force on that system. No external impulse means no change in momentum of that system. We're going to use an example to illustrate that here in a minute. We're going to examine that principle with this. So let's look at this one. We have a track consists of a frictionless XY where a quarter circle of radius R and a rough horizontal section YZ. A block of mass M is released from rest at point X, slides down the curved section of the track, and collides instantaneously and inelastically with identical at block B. And the two blocks move together, so they're stuck together to the right, sliding past point P, which is the distance L from point Y. L, let's just call this L. The coefficient of kinetic friction between the blocks, so there's a coefficient of, it's a rough part here, is mu K. Express your answers in terms of M, L, mu, R, and G. Determine the speed of the block A just before it hits block B. So the first part is not a collision, right? So there's kind of there's a lot of things happening in this problem. Things are sliding down the ramp, they're colliding, they're moving to the right. So there's kind of a lot of things to think about. The first part they're walking you through is talk about what is it doing as it's moving down this curve. Now this one, we're actually going to do conservation of energy. And I want to think about why we can do conservation of energy. If I were to draw the free body diagram of the block at just any point in time, what I would say is, oh, well, there's definitely gravity, and there's definitely a normal force from the surface, but nothing else is touching the block. Those are the only forces acting on the block. Okay? That's it. This is why free body diagram is so important. If you can't do a free body diagram, it's really hard to understand the core principles of some of these later topics. Okay, so mg, I would say, well, I don't have to worry about mg if I include the Earth as the system. So I'm going to say, well, let's say it's a block plus Earth system. So this is about energy. So the mg, I don't have to worry about it doing work. Okay, the force is clearly there. It's just not doing work on my system. Remember, with energy, I care about whether or not there's work happening. Now, the normal force. Why doesn't the normal force do any work? Is because the normal force is perpendicular to the direction of motion. Remember, one of the key principles I talked about in the beginning of work is that the force must be parallel in the direction of motion. It must have a component parallel to the direction of motion. If the force is perpendicular to the direction of motion, just like the normal force is in this case, then the normal force does not do work. Okay? So there's no work acting on it because neither of the forces are considered to be work on our system. Okay? There's no work on our system. There's no change in energy of our system. Now, if there were friction, if there were a frictional force, like opposing the motion of this block sliding down this way, then clearly friction would be doing some work. Then I couldn't say, I can't use conservation of energy anymore. I can't say the energy is the same. I would not be able to invoke that. But there's no friction here because they said it was frictionless. Okay, so then I want to do the energy here at point. The energy here has to equal the energy here before the collision. If I say this is my height equals 0, and the block, is it released? It's released from rest, right? So there's no speed up here. So it has no kinetic energy up here. It only has gravitational potential energy. That is mg. And what is the height? It is above the ground is r, the radius of the circle, mgr. Right? Because I want to know how high he is above the ground. Okay, and then down here, he only has kinetic energy, right? Because he's at a height of 0. The block is right here. Height of 0, so it only has kinetic energy, so the E final is 1/2 mv squared. And so we just set them equal to each other. I would say mgr equals 1/2 mv squared. The m's cancel. I multiply by 2. And so v is root 2gr. Okay? Determine the speed of the combined blocks immediately after the collision. Okay? They both have the same mass, right? So, okay, so yeah, they're identical blocks. Okay, so same mass. So here, with the collision, we want to say, I'm going to include both objects in my system now. So this is the block A plus block B system. So during this collision here, okay, they collide. All right, they exist a force on each other. But if I look at all the forces of the system together, so not on the forces they exert on each other, that's internal. Any external forces on the system, I'd have mg and I'd have a normal force. And so there is no horizontal force. Okay, no horizontal force means no impulse, because if F is 0, then there's no impulse. No impulse means no change in momentum. Okay, so that means the initial momentum equals the final momentum. We do conservation of momentum. So we want to do the initial momentum, which is the momentum before the collision. And then we want to do PF, which is the momentum after collision. Okay, so what is the momentum before the collision? Let's kind of re-illustrate the picture. Before the collision, this guy's moving at root 2gr. And then we have another block that's just sitting here. Okay, so the initial momentum, the way you do is you just add the momentum of every object in the system. Momentum is a vector quantity, though. So you do need to put a sign. You need to assign directions, okay? Unlike energy and work and energy are not vector quantities, if I didn't explicitly state that. So we don't have to talk about directions so much, other than positive or negative based on the directions being the same for work. But like, we don't talk about there's a positive energy, or we don't talk about the energy having a direction. The kinetic energy is just a value it has. But momentum is a vector quantity, so it does matter the direction. So let's say right is positive. The total momentum would be m, the mass of this guy, times this, his velocity, plus the mass of this guy times his velocity, which is 0. So the initial momentum before the collision is m root 2gr. Now the two blocks are stuck together, and they're both moving some unknown velocity v. Then I would say the final momentum, again, is the sum of the momentums of every block. It's m times v plus m times v. And they're both moving the same speed, so it's just 2 mv. So they both have the same v because they're moving together. They're stuck together. And then by conservation of momentum, I just set them equal to each other. I would say m root 2gr equals 2 mv. Divide by m, the m's cancel, and then divide by 2. V would be root 2gr divided by 2. Okay? Assuming that no energy is transferred to the track or to the surrounding blocks, determine the amount of internal energy transferred in the collision. Okay? So a lot of times in collisions, we might lose energy. Okay? If we lose, let me take that back a little bit. We lose mechanical energy. There's other forms of energy out there. There's heat energy, there's light, there's sound, there's nuclear energy, there's energy in foods. There's all forms of energy out there. But in this class, we're concerned primarily with mechanical energy. And in a collision, we want to talk about whether or not there's any loss in mechanical energy. Any loss of mechanical energy has to be converted to some other form of energy. Okay? And that could be as like heat, but they're saying no energy is transferred to the track or surrounding the air blocks. That means the energy has to just go into the system internally somehow. Okay? So in this case, what is the energy transfer? That is, another word is, if there's a difference in the mechanical energy, that energy had to go somewhere to the internal energy of the system. So in a collision, we look at the energy, kinetic energy before the collision. So let's look at the kinetic energy here. I'm just going to add up the 1/2 mv squared of every block. 1/2 m times root 2gr squared plus 1/2 m times 0 squared, because this guy's not moving at all. So the kinetic energy before the collision is 1/2 m. When I square this, I just get rid of the square root. The 1/2 and the 2 cancel, I just get mgr. Right, so that was the kinetic energy before the collision. After the collision, each block, is like this. The velocity is half, basically. So I just add the kinetic energy of each block. They have the same kinetic energy because they're moving the same mass and same speed. But I'm literally adding the kinetic energies of both blocks. And if I do this, I square this guy, it's going to be 2gr. I square the 2 on the bottom, it's 4. Right? Then let's see, this 1/2 and the 2 cancel, 1/2 and the 2 cancel. So I get 1/4 mgr and 1/4 mgr, which is 1/2 mgr. Right? So what was the change in energy is the kinetic energy of the final minus the kinetic energy of the initial. That means we lost energy here, because I ended up with 1/2 mgr and I started with mgr. And so I lost 1/2 mgr. The positive or negative is not a super idea. It doesn't really matter. Basically, the amount of energy transfer technically is just the positive amount, because minus 1/2 mgr means I lost that much energy. That means that must have gone into the internal energy, or must have gone somewhere else. But the big thing to really think about is we had a change in the energy. The energy was lost. Okay, so we lost 1/2 mgr of the kinetic energy during the collision. Okay, so keywords. If the kinetic energy changes before and after the collision, if there's a change in that, then the kinetic energy, then we say the collision is if it changes, we call it an inelastic collision. If the kinetic energy stays the same before and after, we call it an elastic collision. So you actually, whenever you're asked to justify about elastic or inelastic collision, it's not about whether they stick together or not. It's about whether or not the kinetic energy before and the kinetic energy after are the same. Okay? All right, cool. Determine the additional thermal energy that is generated as the blocks move from Y to P. So whenever you're talking about thermal energy, I don't know if they'll do that too much anymore. This is kind of old style talk about it, but any work done by friction generates thermal heat. And that's why when you rub your hands together, if you're cold, you rub your hands together, right? That warms up your hands, right? That's because you're using friction to generate heat. So work done by friction generates thermal energy. That's the one thing we think about. So if I want to ask about the thermal energy, I want to consider what is the work done by friction in this scenario as it goes from here to here. Okay. Now, you could do, there's a couple ways you could do this. You could you could just do the force of friction times the displacement. Okay, that's one way you could do work. Or you could say the work done by friction causes a change in the kinetic energy or change in the energy of the blocks, right? Because as these blocks are sliding along, they're moving to the right, right? The displacement is to the right. That's the displacement. And if I do a free body diagram, I'm going to have mg. I'm going to have a normal force up, perpendicular to the surface, and I'm going to have a frictional force to the left. Okay? So this frictional force here does negative work because the frictional force is opposite the direction of the displacement. So you could talk about the change in energy, or you could do force of friction times the displacement. Either way, technically, it doesn't really matter which way you want to do this. Let's do it one way, as directly as the work done by friction. Work done by friction is going to be the force of friction times the displacement. It's technically negative. Friction does negative work, by the way. Force of friction is equal to mu times Fn, which is mu. In this case, because the vertical forces add to 0, because it's not accelerating vertically, the normal force is going to equal mg. So you would say this is negative mu mg times L. And that would be fine. You could just leave it like that. That would be one answer you could do. That is the work done by friction. That is the energy lost by friction. So that's for part D here. You could have also looked at it as the change in the energy. But I think this is the most direct way because I wanted you to use mu. Yeah, you could have also done the change in energy. You could have done I think an alternative answer could have been the change in kinetic energy because it. Oh, actually, did it come to a stop? Oh, they slide past point P. Okay, so you couldn't have done the change in energy because you actually don't know how fast it's moving at this point. So you would have to do it this way. So work of friction. Someone asked if it's 2 mg. That's right, it is 2 mg because it's 2 blocks. So it should be 2 mg. That is correct. It should have been a 2 mg. Why? Because it's both of the blocks are. It's the blocks, not just a single block, but both blocks. Ah, okay. Why is work done by friction negative again? Okay, so let's do the. So it has to do with the direction of the forces. Okay. Frictional force is acting to the left because if you have that friction, so the blocks are sliding to the right along the surface, so frictional force is pointing to the left, but the displacement is to the right. Okay. So if the force and the displacement vectors are opposite directions, then the work is always negative. If the force and the displacement are in the same direction, then it's positive work. Okay. So like, let me give you an example. So a train is, Superman's trying to stop a train. Train has a lot of kinetic energy, right? So he needs to take away that kinetic energy. He needs to make the change in energy negative because he wants it to have a lot of energy and then he wants it to have no energy afterwards. So he wants to do negative work on the train. How does he do negative work on the train? Is he pushes against the direction that the train is moving. That's how he's going to stop it, right? And that's would be negative work because it's going to end with no kinetic energy if he stops it. And it has a lot of kinetic energy to begin with. So he wants to push against the train. As opposed to if he wanted to do positive work on the train and he pushed it in the direction that the train was going, then he would be giving the train kinetic energy and making it go faster. So positive work will increase the energy or, cause an increase in the energy, and negative work will decrease the energy. Similar thing here, friction is going opposite direction of the motion. It is slowing down the object, taking away the kinetic energy of the blocks. Okay. I hope that answered that question. Okay, cool. All right, let's do harmonic motion. Harmonic motion is nothing more than conservation of energy for the most part. except we have some period equation involved. So we're just going to do another one that's kind of related here. The period so there's two kinds of harmonic motion we talk about: mass on a spring, and this is the period of the period equation is 2 pi root m over k. Okay, that means the period is dependent on the mass of the block and the spring constant. When I say harmonic motion, this is where it's oscillating back and forth. There's also one for a pendulum, which is t is equal to 2 pi root L over g. This is not what this problem is, but that's with an object that's swinging back and forth like this, okay? So we're not gonna have time to go over one of those examples, but that is a pendulum scenario. And that's the period for a pendulum. It's based on the length of the string in g. Here, this is a period for a mass spring system, mass spring oscillation. Those are the two kinds of harmonic motion we really talk about in this class, okay? There are other forms of simple harmonic motion, by the way. It's just in this class, we're only gonna talk about these two. All right, so let's just go through the problem. One end of a spring constant K is attached to a wall, and the other end is attached to a block of mass M. As shown above, the block is pulled to the right, stretching the spring from equilibrium position and then held in place by a taut cord. The other end, which is attached to the opposite wall. The spring and the cord have negligible mass, and the tension of the cord is Ft. Friction between the blocks and the surface is negligible, so no friction. Express all answers in terms of M, K, Ft, and fundamental constants. On the dot below, it represents the block. Draw and label free body diagram for the block. Okay, free body diagram time. I got gravity. What's touching the block? Well, the ground is touching it, so there is a normal force going upward. Okay, we got a spring. Now, what did we do with the spring? We stretched the spring, right? The spring was sitting here all nice and happy, and we stretched it. It wants to go back, so it's going this way. This is a force from the spring. What else is touching it? The cord is touching it. The cord is going to pull to the right because ropes can only pull. Strings can only pull. That's it. That's the free body diagram. See how we did that? We talked about everything that was touching. Okay. B, calculate the distance the spring has been stretched from equilibrium position. Okay, so that's how far the spring has been stretched. Well, what we're normally going to do is F net equals MA. That's the next step on a free body diagram. Okay, the A is 0. Because it's just sitting there, right? So it's held in place. Held in place means not moving, right? Not going to accelerate. I'm not oscillating. It's held in place here. So I'm going to focus on the x direction. Let's say right is the positive direction. As arbitrary, I picked a direction. So when I did a net force, I say to the right is Ft is positive. Spring force to the left, it's negative. And that equals m times a, but the a is 0. So therefore, the spring force equals Ft. Okay, that's pretty good because I know that the spring force is related to its equilibrium position. Remember, the spring force is Kx. So, now I can find what x is. X is how much it's stretched. X would just be Ft over K. Just divide both sides by K. Awesome. Now the cord suddenly breaks, so the block initially moves to the left and oscillates back and forth. So now it's going to oscillate back and forth. Calculate the speed of the block when it's moved half the distance from its release point. Half the distance from its release point to its equilibrium. Okay, so this is the released point. Let's say the equilibrium position is here. We'll say this is the relaxed length, equilibrium. Equilibrium is where the net force is 0. So in this case, it would just be where the spring is at its relaxed position. And so then we would say, oops, it's not oscillating from that there. So let's say, yeah, this is the released point. And here what we're going to say is this distance we just found was Ft over K. Because this is how much I've stretched it. Okay, so I've stretched it, I've cut the string now, and I've released it. And so what's going to happen is the block mass is going to go between here and here. Okay? So calculate the speed of the block. They want the speed of the block not at the equilibrium position, but right at this position here. Okay? This distance is 1/2 Ft over K. Okay? And they would like to know how fast the block is moving when the block is moved halfway between there and the equilibrium position. Okay? So the key thing you always want to do with harmonic motion like this is we're going to do conservation of energy. Okay, so we're going to say the energy here equals the energy at this point right here. So the initial energy that we're going to be talking about here. So what forms of energy do we call? If I include the block and the spring, which is almost always what you want to do when you're doing a harmonic motion, kind of this, is oscillating. I want to consider the mass and the spring together as a system. And I'm basically saying the energy is conserved the whole time because there's no work happening on the system. So I basically want to just say energy is conserved. So what forms of energy here? Well, I just released it at this point. I've cut it right here. The velocity is 0 at this end point. So it only has spring potential energy, 1/2 kx squared. And we just calculated what that was. The x was ft over k. Okay. That's the energy at that position right here. Then I want to know what is the energy here, because if I know the energy here, or I know the kinetic energy, I can solve for the speed. Okay, so this is the initial energy. The final energy has two forms of energy, because at this point, the spring is still stretched, not as much, but it's still stretched some. It's stretched this amount, right? Because it's not at its, the spring is halfway to its equilibrium position, so it's still being stretched, just less so. So here it has two forms of energy. A spring energy and a kinetic energy. Has two forms of energy. Now, what is the displacement at that point? How much is the spring being stretched? It's half of the displacement all the way to the end point. Oops, that was badly written. Ft over k plus 1/2 mv squared. Let's simplify this guy here. This is going to be 1/2 k ft over k, ft squared over k squared. One of these k's will cancel, so I get 1/2 ft squared over k. So I was just working on that initial one, and then here's the final one. Let's simplify this guy. This would be 1/2 k. I got to square everything in here. Squaring the 1/2 is 1/4. Squaring the ft is ft squared. Squaring the k is k squared. Similar to this one of these k's cancels, and then this guy's going to be, oops, sorry. This guy's going to be 1/8 ft squared over k plus 1/2 mv squared. I know this is like a lot of an algebra mess. One thing I want to emphasize to you, you mess up the algebra here, it's okay. If you get the process right, you get credit for demonstrating you know the right principles to apply. Okay, so don't give up just because you're like, well, I don't know if I can solve all this. You write all this down. You get like, usually a derivation is like 3 points. The right answer is only one of those 3 points. You can get 2 of the points just by having the right setup here. And then finally, we're going to say the energy is conserved. 1/2 ft squared over k. So we're basically saying the initial energy, which we got here, is the same as the final energy that we got here. Okay? So we're going to subtract this to the other side. 1/2 mv squared equals 1/2 ft squared over k minus 1/8 ft squared over k. And then I'm going to multiply through by 2. That might make it easier. So I get mv squared is ft squared over k, because 2 times the 1/2 would cancel, and 2 times 1/8 would be 1/4. 1 minus 1/4 is 3/4. So this is 3/4 ft squared over k. Because it's like I have one of these and I take away 1/4 of these. And then I divide by m and I take the square root. So I'm not going to spend too much time on the math there for mk. Put the m on the bottom and then take the square root like that. And just leave it like that. Okay? So this one was tricky because usually they ask you what's the speed at the equilibrium position. But here they ask you for the speed at a different point. Same principle, though. If you know the principle is conservation of energy. If you want to say the energy here equals the energy here. Okay? Calculate the time after the cord breaks until the block first reaches its furthest position to the left. So that means how long does it take to go from here all the way to the most left position here? Okay. Now, this is where the period equation comes in. The period is the time it takes to make one oscillation. That means go to the left and then come back to where it started. So to just go from the end all the way to the left is only half a period, 1/2 t. So I would say what I want is 1/2 the period, which is 1/2 2 pi root m over k. Okay, and the 1/2 and the pi cancels, and yeah, you can just do an m and k. So this would just be pi root m over k. So that is that one's actually really easy. The purity equation is pretty straightforward. It's just 2 pi root m over k, but that time is the time to go all the way there and back. To just go there is half the time. So suppose instead that friction is not negligible and that the coefficient of kinetic friction between the block and the surface is mu k. After the cord breaks, the block initially again moves to the left. Calculate the initial acceleration of the block just after the cord breaks. Okay, so just after the cord breaks. So they're saying now that there's some friction. And yeah, okay, so they're just saying that you break the cord, but there is some, they just want the initial acceleration. Okay. So that means if you were to draw your free body diagram, what's changed is there's no more tension. The cord is gone. You still have the spring force to the left. Now, because it's starting to move to the left, it's beginning to move to the left, you're going to have a frictional force to the right. Because it's going to oppose that motion. Because now, so basically they're saying we do have some friction, some kinetic friction with the surface. So as the block is sliding left, there's a force to the right from the friction. And they want the acceleration. So we're just going to do F net equals ma. Let's say the acceleration is to the left. We'll say left is the positive direction. That's arbitrary, by the way. I'm just saying it's to the left. You could do right is positive. But I know that the block is about to slide left, so that's why I usually pick left as positive in this instance. So the net force would be the spring force is positive. The frictional force is negative because it's moving to the right, and that equals ma. The frictional force is equal to mu Fn. Right, that's our equation for friction, for kinetic friction. And that is mu times mg. Because in the vertical direction, the acceleration is 0, so these two forces are equal. Okay, so you can plug that into there, and you'd have the spring force, which is kx minus mu mg equals ma. And then we found what x was. It's ft over k. So you can put... Oh, yeah. Wait, no. Yeah. We could just say ft over k. Because I don't think they gave us any new variables. So we still want to put everything in terms of these. Even though the chord isn't there, I think they still want you to say, like, oh, it's k ft over k minus mu mg equals ma. And so then I think you... Yeah, I think you just divide by m. Divide all that by m. Sorry, we're running low on time, so I want to make sure that one's not a huge deal. That was just like this problem was again another free body diagram problem with forces, and just do F net equals ma. Okay. All right, you guys are troopers for staying in there. I know this is tough. I know this is like a lot to cover in a short amount of time. So you guys are, thanks for hanging in there, and thanks for taking the time this Saturday to be with me on this one, because I know like. It's a lot of time to sacrifice on the weekend for you guys. So I do appreciate your time here. Okay, last part is rotation. Rotation I consider a pretty big unit. It's probably more recent, hopefully, so maybe not as much of a review, but we're still going to go through some problems, and I'll give you a little bit tips on certain things as we're doing them. Okay. Wooden wheel of mass. So the big thing, so rotation, the way you want to think of rotation is there's always an analogous form for everything we're talking about. If I were to really focus on rotation, you don't have a lot of time, I would really focus on your angular momentum, rotational energy, and torque, making sure you understand those kinds of aspects. The kinematic, like basically in rotation, all of the units we covered, except for harmonic motion, there's basically rotational versions of everything in there. Okay, so like, for example, for kinematics, the 5 variables we use for kinematics are these, instead of the linear equations, right? Okay, this is the angular velocities, this is angular acceleration, angular position. Same thing, same kinematic equations, just we use different letters for them, basically, to describe the rotational forms of them. And there's always a connection between the tangential, like kind of the linear speed, and the angular speed. Like, for example, there's always like these equations here. Like the distance is r delta theta, the linear velocity is r omega, and the linear acceleration is r alpha. These kind of equations are not given on your equation sheet on the AP Physics 1, but they relate the linear motion to angular motion. Okay, that's what I would say for kinematics, is pretty much just that. The hard one is when we're doing torque. Net torque equals I alpha. This is probably the hardest one to do. When you calculate torque, you're doing RF, and they have to be perpendicular to each other. So unlike work, with work, you're always talking about like the force parallel to the displacement. With torque, you're talking about the R and the F being perpendicular to each other. Okay? Now, the only difference on a free body diagram problem when it relates to torque is that we need to draw the force where they're acting. Okay? Otherwise, the free body diagram is identical. The forces and the directions are the same. We just need to talk about where they're acting at any point in time. So we have a wooden wheel of mass m. Is rolling down. It makes an angle here. The ramp exerts a force of static friction on the wheel, so the wheel rolls without slipping. On the diagram below, draw and label forces that act on the wheel as it rolls down the ramp, which is indicated by the dashed line to clearly indicate the point of the wheel. Yeah, they're just telling you draw all the forces. So now we want to draw not just at the dot like we've always done, like at the center. We want to talk about where the force is acting. So for this guy, when we talk about gravity, gravity always acts at the center of the object. Technically the center of mass, but center of mass is almost always the center of the object. So I do gravity, but I put it right at the center here. The normal force exerts where it's at contact. So it's like here, like this. And it's perpendicular to the ramp, because the ramp is touching it. Now the static friction, this one's a little bit tricky. The static friction is this way. And it has to do with the fact that the static friction is the only thing that can exert a torque on this system. And we're going to talk about that in a second, why the frictional force has to be this way. Because this thing needs to, the angular acceleration needs to be this way so that this guy can roll without slipping. If the angular acceleration is clockwise, then the frictional force needs to be here to cause that wheel to rotate clockwise. So that's why the frictional is that direction. Okay, and that's the free body diagram. That one's a little tricky. Let's talk about why the normal force and gravity don't do any torque. If you want to calculate the torque, what you have to do is you have to identify an axis of rotation. And in this case, the axis of rotation is right at the center of the wheel. So the center of the wheel is the axis. And when you calculate torque, you do the R and the F perpendicular to the R. Now, what does the R represent? This is the really important thing to recognize. The R is the distance. It's a vector from the axis of rotation to where the force is applied. I cannot emphasize enough how important that is. Rotation to where the force is applied. This is why we need to put the free body diagram forces where they're acting. So, I didn't explicitly say it, but where the forces are acting is where they're actually touching. Hopefully that makes sense. That's why I put the frictional force down here and the normal force down here, because that's where the wheel is touching the ramp. Gravity is the only one that doesn't require physical contact. It acts as the center of the object here. Okay. So in this case, what we do is we draw an R vector. Well, for the gravitational force, it's acting at there. So the R is 0, because if I draw from the axis of rotation to mg, that R is 0. So it doesn't exert a torque. If I look at the normal force, I draw a vector from here to here, from the axis of rotation to where the force is applied. The normal force is not perpendicular to the R. And you need a vector perpendicular. Like if I want to rotate something, I have to act perpendicular to that R vector. See, like if I have my pen here and I want to rotate it, I got to push down this way. I can't push this way on it. I can't push parallel it. So because the R is parallel to Fn, it doesn't exert a torque. So the only way this guy will spin is because there's a friction. There's an R and an F going this way. Now, should the F go up the ramp or down the ramp? Well, if it were going down the ramp, it would cause the wheel to rotate counterclockwise, which is not intuitive, because if the wheel rolls down the ramp, it's going to rotate in the clockwise direction. That's why the frictional force is that way. As the wheel rolls down the ramp, which force causes a change in the angular velocity? So what's causing the torque? It is the static frictional force. And the explanation is everything I just said to you. Fn can't exert a torque because it's parallel to the r vector. And mg acts at the center of mass at the axis of rotation. It also doesn't exert a torque. So static frictional force only exerts a torque. And I'm not going to write it all out just because we're a little bit, I don't want to go too long over on the time. If you guys have to go, feel free to go, and I'm going to keep going, and the recording will keep going. Hopefully it won't stop you guys until I end it, I think. I know it's scheduled to end at 3, or 3 Pacific time, but in a few minutes, but I'm going to go ahead and finish out this problem at least. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction. Instead, the magnitude of the force of static friction is 40% of the magnitude of the force or force component directed opposite the force of friction. Derive an expression for the linear acceleration of the wheel's center of mass in terms of that. So this is actually just doing net force equals ma, because if I want the linear acceleration of the mass, I want to do F net equals ma. So let's look at our forces here. Let's just redraw it again, just without, like, without the positional information. Right? Like, it's like that. And so I know it's accelerating down this way. And so I'm telling you it's this way. And so I want to decompose my forces, my mg, remember, into the, just like the inclined plane stuff we did earlier. This is mg cosine theta. This is mg sine theta. Right? Sine is the opposite, right, of that angle. And they're saying the force of friction is 40%. 40% of what? The force directed opposite the force of friction. Which force is directed opposite the force of friction is the mg sine theta. Okay, that's what they're telling you, right? It's 40% of what? 40% of the force opposite the direction of the force of friction. So then when we do net force equals ma, down the ramp, if I say down the ramp's the positive direction, mg sine theta is down the ramp. Force of friction is up the ramp. Those are the only forces in the x direction. That equals ma. This is 0.4 mg sine theta, like we just said. This is mg sine theta. So the difference here is just 0.6 mg sine theta. And that equals ma. The m's cancel, and I get 0.6 g sine theta for a. Okay? So same process. If you can draw the free body diagram, if you can apply net force equals ma, and you can set this up, I actually don't care if your algebra is not that good on this part and you get this part wrong. You will get all that credit for that setup there. Okay? All right, second experiment on the same ramp. Block of ice, also with mass m, is released from the same instant the wheel is released from rest, from the same height. The block slides down the ramp with negligible friction. Which object of either reaches the bottom of the ramp with the greatest speed? This is an energy question, okay? And this is an important concept on energy question. So if you want to think about, well, actually, they want you to answer in two ways. One in terms of forces, one in terms of energy. So the block of, if I look at the block of ice, and I look at the forces here, there's no friction on this one. Friction is causing this guy to slow down a bit, right? So just from forces alone, for the block of ice, because there's no friction, the block of ice is going to accelerate down faster. I would say the block. And in terms of forces, there's no friction, so the net force is larger down the ramp. Okay? That's why this is a little counterintuitive. You think the wheel would go faster, right? But if there's no friction with the ice is definitely not going to have any friction, not going to have anything slowing it down as much as the wheel does. Okay? Now we do in terms of energy. Well, this is the thing. Both objects are going to have conservation of energy involved. If you include the Earth as part of the system, you say they start at the same height, they have the same mass, they start with the same gravitational potential energy. The difference is this block converts all of that energy into translational kinetic energy. Okay? Linear kinetic energy. This block doesn't have any work happening on it. And so what it does is, but it has some energy related to the fact that it's spinning. So we didn't talk about the energy of spinning, but when something is spinning, the kinetic energy of the rotation is 1/2 I omega squared. But in principle, this is what the basic idea of this question is telling you, is the fact that as it's rolling down the ramp without slipping, it's converting that potential energy to both kinetic energy translationally as well as rotational energy. The energy has to be split between some of it spinning and some of it just moving down with acceleration. Okay? So from an energy point of view, we would say the energy is split. So for the wheel, the same potential energy is split between rotational kinetic energy and translational kinetic energy. Whereas for the block, all of the energy just goes into translational kinetic energy. Okay? Awesome. Okay, we did hit all the topics. I had one more FRQ that I was going to go through related to angular momentum. It's probably going to take another 10 to 15 minutes. Like I said, if you guys got to go, I'm going to go ahead and record me doing the rest of that question. It'll be on the recording. But if you guys have to go, I could understand. I don't want to like take up any more of the time that you've already given to me today. So I hope if you got to go, I hope you found that helpful. Like I said, the recording will catch the rest of this. If you guys got to go, you got to go. I understand that completely, okay? But I'm going to continue on with this last question here. It's a long question. Suggested time's 25 minutes. Probably going to take me about 15 minutes to wrap this up. Okay. Here we have a left end of a rod of length d and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot as shown above. Point C marks the center of the rod. The rod is initially motionless but free to rotate around the pivot. So I'm going to slide this massive disc and I want to hit it and cause it to rotate, basically. He wants the rod disc system to end up with as much angular speed as possible. Suppose the rod is much more massive than the disc. To give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C, the right of point C, or at point C? Okay, and why would we say this? Well, intuitively, hopefully you know, if I want this thing to rotate, I want to hit it further over to the right here. Now, why do I want to do that? Well, imagine that it's going to apply it. So if I want to cause something to spin, I need to exert a torque. Torque is equal to I alpha. That is necessary to cause something to spin. Okay? Now, why? Because I need a torque to cause an angular acceleration. That's what I want to do here. I want to change its angular velocity by exerting a torque. Remember the torque is related to where the force is applied, but how far the distance from the axis of rotation is, right? Torque's equal to that RF, R perpendicular to F. So if it's going to be the same force, because I'm hitting it with the same disk with the same speed, I want it to be a larger R to exert a larger torque. And so I want this to be as far to the right as possible to exert the maximum amount of torque. Okay? So there's more torque if the same force acts at a further distance, further R from axis of rotation. Okay. On the internet, a student finds an equation, blah. It doesn't really matter what the equation is. Regardless of whether the equation is correct, does it agree with your qualitative reasoning in part A? In other words, does the equation for omega have the expected dependent as reason in part A? Okay, this is an important concept I want to talk about on the AP Physics exam. when they're asking you to understand an equation and interpret an equation, or to whether it makes sense, they're asking you about if the variable dependency is correct. That is, if one variable goes up, does the other variable also go up or go down, and does that make sense? So what we just said is the dependency I just explained in part A analytically say is if x is larger, then omega should be larger. That's what I basically said in part A. I basically said I want x to be bigger to exert a larger omega. So you don't care about any of the other variables. You're just asking about the relationship we talked about is x, the position I put it at compared to the angular speed. That's what you want to focus on answering a question like this. Focus on that relationship. And here, if x is bigger, omega goes up. So I would say yes, because a larger x results in a larger omega, which is what I said in part A. That's what I was looking for. Okay. Another student derives some equation. Bloss, again, we're analyzing an equation. So this is what the QQT question is about. One of the free response questions, you're going to get something like this. They're going to ask you to analyze the relationship or understand an equation. They're going to ask you to derive an equation or look at an equation and see if the dependence is correct. Without deriving the correct equation, Hauke-Tell's equation is not plausible. In other words, it does not make physical sense. Briefly explain your reasoning. Again, we want to talk about dependency. If one variable goes up, how should it affect the other thing? So you want to look at each variable one at a time, and I might just pick something that's easy. So we're not going to talk about, so the x seems to be fine, right? If x is bigger, omega is bigger. How about v0? If v0 is bigger, should omega be bigger? Well, v0 is how fast I fling the puck, right? If I fling this faster, is it going to cause it to spin faster? Probably, right? So the v0 is not an issue. How about the mass of the disk? If the mass of the disk is bigger, what should I expect to happen? Well, if I throw it with the same speed, but I throw like a giant bowling ball at this thing instead of a little puck, I would expect it to hit it harder and make it go faster. I would expect as mass of the disk increases, the speed should increase also, right? And that's not what happens here. Because if I put a bigger number on the denominator, it makes omega go smaller. So this says the M disk is an error. Is wrong. Because as M disk increases, a larger torque will be exerted. Torque is exerted, so it should move faster. So it should move faster. And this equation doesn't do that. That's what you should say. Okay? That's the kind of reasoning you want to put in that kind of question there. You want to talk about dependencies. There's also a problem with I. Let's just talk about rotational inertia because I want to give you a little bit of teaching on that. I is how difficult something is to rotate. The larger I is, the harder it is to rotate. So if I is larger, then when I hit this thing, it shouldn't rotate as much because it's like it has a larger I. It's harder to rotate. And so the I is also wrong here because if I increases, it should have been hard. You don't have to recognize that one. And this one, either answer would have been fine. If you recognize the mass of the disk or the I, there's a problem. But just so you know, the I is also an issue. But you didn't have to label one or the other. I mean, you didn't have to do both. You could have picked one or the other. For parts of D&E, do not assume the rod is much more massive than the disk. Immediately before colliding with the rod, the disk's rotational inertia about the pivot is mds disk x squared, and its angular momentum with respect to the pivot is this. So they're giving you the rotational inertia, and they're giving you this. Derive an equation for the post-collision angular speed of the rod. Express your answers in terms of this as appropriate. I'm going to actually redraw this picture just so you kind of like see what's happening. And they're sticking together, I think. The student was like the student. Okay, yeah. Actually, they didn't say. Okay. So I think in this one, I don't remember where it said it, but I think it said it did stick. So what we want to do is, oh shoot, my OneNote's acting up real quick. Don't die on me. Sometimes when I put too many images in here, it does tend to crash real quick. So let me pause my sharing real quick and redo this. Sorry about that. Just had to restart my OneNote. Okay. All right, cool. So derive an expression for the post-collision angular speed. So we have a collision happening. A lot of times what we want to do with collisions is we want to talk about, you know, with collisions with linear motion, we talk about conservation of linear momentum. Here we want to do conservation of angular momentum, right? So we have a similar equation for rotational motion. An impulse, like in linear motion, we talked about this. An impulse causes a change in linear momentum. Here we call an angular impulse causes a change in angular momentum. In linear momentum, P was equal to mv. Here, L is equal to I omega. So there's kind of a relationship between a lot of these rotational variables. Instead of force, it's torque. Instead of P, it's angular momentum. Instead of M, it's I. Instead of V, it's omega. So like there's like this analogous versions if you kind of think about all the rotational variables. But anyway, that's the basic idea. So here I want to do the L before the collision. The initial angular momentum equals the final angular momentum in this, if I include the kind of the rod and the disk system. So they're saying the rotational inertia is this, and the angular momentum. So prior, the initial angular momentum is the angular momentum of the disk plus the angular momentum of the rod. The angular momentum of the disk, they told you, is m disk v0x. The angular momentum of the rod is 0 because it's I omega, I of the rod times omega. But the omega is 0 because right now the rod is not moving. Okay, so it's just, this is 0. Then the final angular momentum is afterwards, they're both moving together. Okay, so this thing is like, I think what they said was in this problem, sorry. The student will slide the rod will stick to the rod. Okay, cool. It sticks to the rod and it moves together. So now it's equal to I omega. But here the I, what you have to do is you have to do the I of the whole system. It's the I of the rod plus the I of the disk. Because they're both part of they're together and they're both rotating with the same angular momentum. So the I of the rod was just I. The I of the disk, the rotational inertia of the disk, they give you right here. Times omega. And then that has to equal the initial angular momentum, m disk v0x. So then you can solve for omega by dividing this whole thing over here. Again, try not to get too intimidated by the math. If you wrote things like this, and like this, like that's a lot of the credit in the derivation for something like that. Like you would get at least half of the credit, even if you couldn't like work out the algebra on that exactly, okay? So consider the collision for which your equation part D was derived, except now suppose the disk bounces off the rod instead of sticking to the rod. So this bounce, so now the disk, instead of sticking to it, the disk now goes this way. Is the post-collision angular speed of the rod when the disk bounces off it greater, less than, or equal to? It's going to be greater because what's going to happen now is, see, you started with the same angular, like we're still going to do conservation of angular momentum. It's still a collision, okay? But so we start with the same angular momentum. But why the final angular momentum here is different because you would add the angular momentum of the rod plus the angular momentum of the disk. But the angular momentum of the disk, he's now kind of rotating in the clockwise direction. So let's suppose this was the counterclockwise, is the positive direction. This is the negative direction. Angular momentum still has a vector direction, clockwise and counterclockwise. So suppose it looked like that. Well, the clockwise direction is negative. So what would happen is rather than the puck having more angular momentum in the counterclockwise direction, it would have some in the clockwise direction. So basically this number would become negative. So that means if it's equal to the same amount as before, this has to be more than before. Like, because the sum of the two have to still equal the same initial amount. They started with the same angular momentum. They have to end with the same total angular momentum. But this guy has some in the positive direction. This has some in the negative direction. So, like, this one has to be even bigger to make up for the fact that this has negative angular momentum. I hope I explained that well. I know it's been a long day and we're kind of tired at this point, but maybe you guys aren't focused. But if you guys rewatch that again, think about the total angular momentum being the same and the fact that this guy now has angular momentum that's negative. So this guy has to have even more angular momentum to make the total the same. Okay. All right. Last things I wanted to talk about with you guys. Final tips. Okay. I talked about this first one just now. When asking if the equation makes sense, you want to compare if the dependency is correct. That means if one variable goes up, another variable goes up too. Okay, that's a dependency that you're looking at. That's the main thing that they're asking you to interpret in those kinds of, if it's an equation kind of based thing. 2, if you can't derive an equation in one part or you can't get an answer of a first part and the second part requires that first one, just show how you would use the answer from the previous part in your next part, okay? Don't get hung up on one part of a question and fail to move forward, because anything you leave blank is like no points that you can earn. So you want to put something down for everything. Even if it's like, even if your answer is like, well, if I knew how to do part A, I could definitely do part B. So I'm going to assume using that. You can even explain that, like, in the space, just say, like, assuming that it's this, right? Then this is what I would do, right? And that can still net you the full credit. The last part is a mistake I see a lot is you get one question that's a paragraph where you're asked to explain or justify. When you are explaining things, they don't want you to have like this long, whatever explanation. They want you to invoke specific physics principles. That means conservation of energy, conservation of momentum, Newton's third law. They want you to use physics terminology, work causing a change in energy, an impulse causing a change in momentum, a torque causing an angular acceleration. They want to use physics principles we talked about today. Not just sort of like, oh, it's pushing and be very vague or like kind of hand wavy in that explanation. They want you to invoke specific physics principles. They're looking for keywords that you're saying in the answer there. So just keep that in mind as you're doing that. Okay? So sorry I went about 20 minutes over. I appreciate, like I said, I really appreciate your guys' time. And I know you guys are here, you guys want to do super well. If you're here with me on a Saturday afternoon, but or evening, wherever you're at. But yeah, good luck on your prep, okay? And just sort of work through more practices. I would say look at a lot of past free response questions. We did a few of the past ones in the recent years. Last year's is an excellent set of free response questions to look at as you're kind of studying and reviewing those kinds of key concepts, and see if you can really master or, execute on some of those principles we talked about today. All right. Thanks, everyone.